Good morning. Thanks for being here, actually. We will continue the things. That is the parity violation experiment conducted by a group of scientists who et al. Who and others, co-authors they can call actually. There are more than two authors. They can say that the et al. It is a terminology, scientific community. On the right side, you can see the portrait. I have a picture of a great scientist, first physicist from China, being a lady who worked on something which is made a landmark in the 20th century on the experimental part on physicists are considered. This landmark they are saying because see landmarks are the landmarks you can't change. You can identify them through the landmarks actually. Landmark that is breaking the mirror means if you see through the mirror, you'll find the image. This is an experiment related something on an like a mirror image they can call it. And what she made actually, how it was made in significance in physics, that we will see in couple of minutes. A few classes, maybe three classes I took on this. We discussed, but we could not able to touch upon what actually it was the work carried out by the professor, the then professor Wu Ching Wu, they can call actually. On red color text, you see that the physics community was stunned or shocked. Maybe amazing is a different. To learn in the 1950s that some events, unlike billiard ball collisions, follow different rules in their mirror image version. If you are in front of the mirror, you have to see your own image. If you are seeing something that got surprised, got disturbed to all. For time being, I will move to last slide. For your interest, I kept one image for you. I will come back. See the image? The same picture I took. In mirror image, you should have a mirror, no doubt. The same woo flipped. The same woo looked like down, upside down. Okay, it is not the upside. It is the downside they can call actually. This type of an experimental result were stunned the physics fraternity and they were shocked why this is happening. And we were not in a position to believe if something is an unusual. Why should we? Because the entire world from centuries together learned the laws, physical laws, laws from the physics side, and even from the theoretical side. They were obeyed by several particles. They were obeyed by several bodies, including galaxies. Right? But if the theory comes in such a way that if they are unable to understand some phenomena, if it obeys in altogether a different way, then it should be a question. What they told is that symmetry breaker means there is a break in the symmetry. Nature loves symmetry. Theoretical physicists are working on symmetry. In fact, symmetry is cherished by the principles in theoretical physics. There is no doubt in it. There are four fundamental forces, okay, that we discussed. Out of that, three of the fundamental force respect the mirror symmetry, means they follow the mirror symmetry, they oblige the mirror symmetry, they accept the symmetry. But Xing, Xing Wu, a lady, showed with radioactive cobalt 60 that an interaction involving the weak nuclear force need not follow the same rules as its mirror image version, which was a huge surprise to the physicists in 1957. Being that, being that we could not able to go ahead with the thing what it was believed for all the three fundamental forces, the fourth force, weak force that exists between the nucleus has had a some kind of a theory or principle that differs from the others. Symmetry is cherished principle in theoretical physics. For example, the mirror reflection of any physical process appears to operate according to the same laws as its real world counterpart. Says if there is a proton, there should be an antiproton. If it is a neutron, there be an antineutron. If it is a matter, let it be an antimatter. If it is an universe, let it be an anti-universe. Let it be an upside object, let it be a downside object. Let it be a left arrow moving towards left, let it be arrow moving towards right. Let it be arrow moving towards up, let it be an arrow moving towards down. All will follow the same trend, same laws, same conservations. Energy gets conserved, mass gets conserved, momentum gets conserved, forces are gets conserved. That is the real part. If something does not obey, then it should be a tough task. Whether only disobeying for that particular thing, or maybe whatever we are accepted so far should have a changeover actually. So it was a huge surprise in the 1950s when researchers showed in the physical review, it's a kind of a journal that mirror symmetry does not always apply. It applies, no doubt, but it does not apply always. There are some exceptions. There are some exclusiveness actually. There are some special category of the objects that we have to understand actually. They found that reactions involving in the weaker nuclear force, such as the radioactive decay, maybe for example, you can take a cobalt 60, they have chosen that one, and violate the parity conservation as the mirror symmetry is known. If all of them are obeying mirror symmetry, that is the conservation of the parity. If something does not obey, the image may not be equivalent to a mirror image. That should be the violation of the parity, or violation of the conservation of the parity. To discover this marked abrupt introduction of the symmetry breaking into the fundamental physics became the challenging issue. Being this, let it be a few slides on the detailed text because you'll also learn how that the experiment has come into the picture. The possibility that the weak interactions which are happening between the radioactive atoms during the decay or which governs the radioactive beta decay and other maybe particle kind of a decays might violate, it might actually, it is not necessarily actually, might violate the parity conservation was not taken seriously by the scientific committee until two young scientists, Zheng Dao Li from the Columbia University and Chuan Ning Yang of Brookhaven National Laboratory, they carefully examined the evidence for the break, evidence for the violation of the conservation. Beta decay is a simple process. Radioactive atoms are, radioactive nucleus are always not stable. They decay. They doesn't have a stability. They decay by the emission of either alpha particle or beta particle. They tested this in beta decay. Whenever a nuclide decays means emits an electron, preferably innermost electrons, like auger electrons they can call innermost or shell electrons may be absorbed. That's one case. Or there will be a possibility of the conversion of proton to neutron and neutron to proton during the beta emission, detection by the emission of an electron. During that, what happens? There should be a change in the parity. That we'll see detail actually. The means these two scientists reported in October 1956 a physical review that parity violations in strong or electromagnetic interactions would be readily apparent. Means they have accepted in past experimental data and could therefore be rolled out. Means there is no violation of the parity in strong nuclear forces or even electromagnetic force of interactions, even from gravity also. But that is not possible in the weak interactions. But for the weak interactions, the available data or available information left the question open in such a way we can't accept that all weak forces are obeyed by the parity conservations or parity conservation will happen for the weak interactions. They also noted that as had the others, including the others, the parity violation might resolve the so-called a kind of a puzzle called tau theta puzzle. But I will explain later in next slide how the tau theta tau and theta are fundamental particles, uh, fundamental particles situated in nuclei. Tau and theta were two recently discovered particles. Recent when? In 1956. Don't get mistake. When we are representing in 2023, it is not the new particles. During 1956, they were explaining in such a way that it was the new finding. Okay, particles with seemingly identical mass, means those masses are same and including the lifetime. They decayed into a distinct sets of particles with opposite parity. That opposite parity we can call odd parity and even parity or mirror reflection property. Means something moves up, something moves down, something moves left, something moves right. They can call it as an asymmetry between left and right, asymmetry between up and down. If the weak interaction did not conserve the parity, fine, the tau and theta would be the same particle decaying in different ways. If it is not conserving, means if the weak interaction did not conserve the parity, means if it is a violation of the parity, okay, certainly these two particles have the same decaying process in different ways. Different means one may be towards left, one may be towards right one. See, while handling with the two negative sentences, be careful. Weak interaction did not conserve parity. If weak interaction conserve parity is fine. Did not, they are saying that. Weak and did not are in opposite, right? Means strong interactions conserve parity, weak interactions did not conserve the parity, means the weak interactions violate the conservation of the parity. Certainly, one can have the expression how they are violating theta 1 theta would be the same particles. Okay, tau 1 theta would be the same particle. Okay, decaying in a different way. There is no distinction between tau particle and theta particle. So, Lee and Yang proposed some experimental test that would settle the matter. So, yes, even if you are having some ambiguity in your theory, you can set up some experiments, you can frame some experiments, you can think of some experiments, you can design some of the experiments, you conduct. That's what required actually. At least you try in the third semester or maybe a vacation in between the semester. I will continue see that one proposal what they Lee and Young they told was to take a radioactive nucleus such as cobalt 60, which has a magnetic moment that can be aligned by a magnetic field. Of course, if any element possesses a magnetic moment, if you're keeping that element in the magnetic field, certainly the particles will be aligned along the direction of the magnetic field and look for an asymmetry in the direction in which the decay electrons are emitted. If that is the case, if there is a decay, for example, decay will happen, electrons will be knocked out. If the electrons are a negative charged particle, being a negative charged particle, certainly they have to move towards the positive magnetic field. Okay, this positive magnetic field gets attracted actually. That they want to try it out. But thing is that conducting such an experiment is not an easy job. With the cobalt magnetic axis vertical, for example, if you keep like an y-axis, okay, more electrons emerging upward rather than the downward. Say, for example, would be the sign of parity violation. If we expect that if the cobalt magnetic axis is vertical in the sense, positive, positive should be more electrons are emerging upward rather than the downward. Means positive, you have to keep it on the top and negative on the bottom. But it is not happening in such a way, it gets reversed. This lady, Ching Wu of Colombia, who had given Li and Yang some early guidance. In fact, Li and Yang worked with the Wu madam, actually, they can call early guidance on their search through the existing data and available data or available information. Tried this experiment because of maintaining the magnetic alignments of the cobalt atoms required very low temperatures. It is a relative terminology, very low temperature of the order of few degree Kelvin actually, in a sense. Who worked out with the scientists at the National Bureau of Standards in Washington, D.C. to place a thin cobalt containing crystal along with the detector inside a cryostat. Cryostat is a chamber maintaining the low temperature. This when she was earlier with some university, she could not able to perform the experiment because of the lack of the facility of achieving the low temperature. She moved to the National Bureau of Standards in 1956 onwards, around 1950 and 50 onwards. Actually, she performed. By the end of the 1956, she and her team were finding a large, they found actually, in fact, large asymmetry in that, but they were not concluded in the sense they found. Even it happens for the most of the scientific community, they will perform the experiments They will perform the theory. They will keep it themselves without publications, without publishing the work to the public domain, scientific domain, in such a way that they may be still thinking of to expect some results actually. By the time still they are waiting, maybe another team may go for publications, whatever they achieve, maybe a pre-results they can call, that they can call it as in a fast communications or rapid communications they can call actually. Journals will accept and publish the work to the scientific community in such a way that that should be their demand, or maybe claiming as the first people who have done that as the first in the world of that kind. See that bottom. Meanwhile, Leon Landerman at Columbia's Navy's cyclotron laboratory, an accelerator actually, had learned from Lee and Yang of an alternative experiment test that involved measuring the pattern of electrons produced by the decay of muons that themselves resulted from the decay of cyclotron generated pions. Means to say, this Leon Landmark, they were doing an experiment actually through the discussion from Lee and Yang, measuring the pattern of the electrons which are produced during the decay of the muons. Muons are subatomic particles, subnucleonic particles. They exchange among the proton and neutron. Exchange of the muons and neutrons between the proton and neutron makes them either the proton or neutron. That we'll see that resulted from the decay of the cyclotron. Parity violation is needed in both of the pion and the muon decays to yield an observable symmetry. And Letterman says that he originally thought of the effect would be too small to see. But when he heard that who had found a large effect, because in 1956 they were finding that a large symmetry they can call actually, he teamed up with his colleague Richard Garvin and the graduate student of Marcel Petrich, like you. Over the course of time, maybe weekend in January 1957, they ran an experiment that produced clear evidence of clear evidence of the party. The Starling, that is not they can call it as a surprise thing. New got out quickly, but who was not yet ready to. They got the result, no doubt actually. Garvin, and a student they can call, he can go to the previous slide. Here I mentioned in such a way. His their colleague actually, they can call his colleague of the Letterman. Okay, Letterman called Garvin, and also a graduate student is another person. Okay? But Garvin wrote, being a faculty, Garvin and I waited. Who wrote actually? Garvin and I waited a very painful week until who had made her last test, says Letterman. Letterman was a person here, you remember here. Letterman interacted with them. Letterman and Garvin interacted, but Letterman wrote the statement in such a way. Garvin and Letterman waited very painful week until who had made her last test, this Letterman. And the two experimental papers which were appeared back to back in the physical review, back to back in a sense, one after the other, whose private communication was the key to our rapid success. In the sense, they discussed, they exchanged their thoughts, they discussed, and their private, because it was not yet published actually, it was not come to the community, scientific community in terms of a journal, they mentioned it as the private personal communications or discussion among them. Yeah, what happened here? Acting with an untypical speed, acting with untypical speed, in the sense not expected in a time arrival, Nobel Committee awarded Lee and Yang the 1957 physics, Nobel Physics. In the sense, acted with untypically speed, in the sense something made them polarized in such a way that they were Nobel Committee was influenced awarded Lee and Yang 1957 Nobel Prize. Means physicists quickly absorbed or accepted the shock of finding that no basic principle was not a fact universally true, and symmetry breaking in many forums is now an indispensable ingredient in theories of particles. Means breaking up of the symmetry is accepted. Unfortunate to hide the work of a who was not recognized for the Nobel. It is not in terms of the recognition for the prize. It is recognition of a scientist who showed the community that violation of the parity in weak forces. Entire world accepted, but she could not able to do that. That was her first invention, but but somehow she could not able to get Nobel throughout her life. Later in about 1887, she got some Wolf Award actually. That's on par with what we can call the Nobel. Yeah. This original curricula in our curricula shows in such a way that we have to discuss on the Wu experiment, particularly the evaluation of the parity from the basic papers, from the original papers. I shared one paper with you right now, but you may not get much out of it because hardly about a two-page material. Always journals will value the space and will not go for detail. Wu gave one talk actually that on the topic the discovery of the parity violation in weak interactions and its recent developments. On 31st March 1983, she addressed and presented actually the work as the Nishina Memorial Lecture at University of Tokyo. This document is available. I took the content from that. She explained in detail about the violation of the conservation in not alone in radioactive cobalt element, but she gave several examples. This is the outcome of, or this is the extract of the talk what she gave. It is available and well documented. You just refer this, why it is happening and how it's happening. On January 19, she started like that. On January 16, 1957, the world of physics was suddenly shocked by the news that parity is not conserved. I told her it was stunned actually. The Jackson professor Otto Frisch of Cambridge University described the announcement as the obscure phrase, parity is not conserved. Circled the globe like a new gospel. Gospel of Wordsworth, gospel of so much of you can see that actually. Okay, we are having such a type of a gospel. Okay, this is which was referred by, for example, even the Bible or Quran or whatever the Bhagavad Gita or something like that. We can follow and adopt actually without going for the fictitious things or without going for what we can call wrong beliefs. We can say that they are the gospels. They are the works actually where one can follow for the betterment. Here also there are the gospels. In the sense, in the scientific community, he was he was made that parity is not concerned, circled the globe like a new gospel. Why has news caused such an excitement? If it is not concerned, why we have to be so excited? Why we have to worry for that? What is the real meaning of the law of conservation of parity? Mass is conserved, you know that mass neither should be created nor should be destroyed. Whatever it is, there will be there. For example, if I bring 1 kilogram ice, it may be converted from one phase to another phase. Ice means that is the solid ice may convert to the liquid water or maybe water vapor, but total mass should remain constant. If assume that 400 grams converted into the water vapor, 600 it should be the ice. Or assume that 400 gram water vapor, some to 300 gram liquid water, maybe another 300 gram of solid ice. Water only changes its phase, like everything actually. What are the implications or what are the consequences of the overthrow of the law of parity on physics? Explain here in the simplest language where it can be understood by the common man. It not be going through the physics actually. It means that the results of this discovery unequivocally prove that many natural phenomena and also the objects of the microscopic world are not necessarily symmetrical with respect to the left. For example, if something is moving towards left as an arrow, if we are keeping a mirror, it looks like it is moving towards right. Something is moving towards right, maybe looking towards left. That's the only thing actually. Now, one must be even more puzzled and want to understand, they decide to understand why people should be so shocked by the discovery in which things turned out not necessarily left, right, but why? Because This symmetry occupies such an important position in the history of the human civilization, even for the philosophers, even for scientists, have naturally attempted to make use of this idea. But the attempt met with little success. For instance, this in 20th century. If you go back to the 1595, of course, go back in the sense, if you go back and search the information available during 1950, 1595, Kepler, a great astronomer, astrophysicist, tried to use the symmetry of geometrical structure to explain the ratio of diameters of planetary bodies. Simple example, take the diameter of all the planets, take the ratio of the diameters. You will come with some number that should be the constant. The six spheres correspond to the six planets, means Saturn, Jupiter, Mars, Earth, Venus, Mercury, means coming from outer orbit to the inner. Saturn to the Jupiter, to the Mars, to the Earth, Venus, Mercury. Then it will fall into this. Separated in this order by how they are separated. The first one is cube, second one is tetrahedron, third one is the dodecahedron, octahedron, icosahedron. This is an unsuccessful way of seeking the harmony or seeking the resonance in static forms such as regular solids by Kepler was long before famous discovery of three dynamical laws now bearing his name. Kepler's law, first law of planetary motion, Kepler's second law, Kepler's third law. Since it was before that he thought, then it was later he gave a three laws. That is different story. What happens? I brought some pictures from the same talk what she made actually. A beautiful picture. Looks like something like that. All are different. About 3 into 4, about 12 objects. This is the snow. Snowflakes are maybe little marvels of frozen water are the best known specimens of hexadecimal symmetry. Why it is hexa? Because 1, 2, 3, 4, 5, 6, like that. Hexa, 6 decimal symmetry. Okay. Uh, penta and hexa like that. 6 decimal. See that left to right symmetry, left to right symmetry, left to right symmetry. In all of them, if you put actually, okay, they were the delight of old and young. Means this shows that some of them are old and some of them are young of that kind. See that cyclic symmetry of a 5 echondromia from the Ernest Haeckel's. This is the form their nature. Their larvae are organized according to the principles of bilateral symmetry. These are for the biological samples. Biological samples. Uh, I'm using this not a licensed version. If another 10 minutes is there, if we log out, kindly log in by 11. This is see that here there is up and down symmetry, not left and right. Here also kind. Here the symmetry on left and right actually of that kind. Here the way here this between these two, not the rest of that actually. Between these two, between these two, between these two. Here left and right, you can see that at least. Here left and right. Here the way between these two. Okay, and here see that this is one kind. This is the palace of the Lagos in Venice that stand for translational symmetry in architecture. See that how that symmetry has made here between these two. See the number of branch, this, arches they can call actually. It is perfectly matched. Here on the maybe top or maybe the left. If we take and let's say exactly the center, the left side here, left side and right side. See, I could have been brought the example of some examples in India, no doubt. But thing is that when they publish, who has worked actually, who has taken some examples, it was known to the scientific community worldwide. She has not chosen the example from India. She has not chosen the example from Pakistan, Sri Lanka, that kind. That's why sometimes while choosing the examples, even though we should not be on par with the Western countries. But thing is that here we are not supposed to do the examples what we want. Yes, it is not of our liking. What they have taken that we have to quote. It is giving what we can call paradigms for their conscience, how they consume. Okay, Let us come to the theory in such a way. The tau and theta puzzle, they can call how it was accepted. How it is accepted means we'll discuss in such a way. Up to about 1956, before they who at all, who and others were discovered this, all theoretical physicists accepted the validity of parity. This parity must be conserved, no doubt. And no experimentalists even thought of disproving the test to challenge its validity. Yes, there were the experiments, several experiments were there for validation of the conservation, not violation actually. Validation means the proving the conservations, for testing the conservations for the all the four fundamental forces, including the weak forces. They were thought of it. In a sense, means, but they are not distinguished actually. But thing is that after 1956, the weakest force, relatively weakest force, has shown some results. That is why this theory came between the two particles, tau particle and theta particle. They called it as a puzzle. Means how if you are unable to solve some problems, we will say that it is a puzzle. Means puzzles can be solved in any way, even sometimes humorous way also, sometimes with the logic, sometimes maybe with some kind of a analysis or analogy. Then the big puzzle in K mesons are the fundamental particles, fundamental elementary particles you can call. Decay, K meson decay came onto the scene to stun the experiment. Stun in the sense to give a big shock to the experts. What happens actually? K mesons are unstable particles, no doubt, which were discovered in 1952 to 53. That is why earlier to 1950, you don't have any thought of the K mesons. You can't explain the structure of the nucleus. You can't explain the structure of an atom. You can't explain the structure of the universe to a great extent. Actually, how it has to happen actually. Means K mesons, discovery of K mesons are maybe identified actually. 50 in 52 to 53, K mesons were discovered. Some K mesons decay into 2 pi mesons. Don't write 2 as the numeral 2 because 2 pi means it is not the two different pi mesons and other in 3 mesons. The K mesons yielding the 2 mesons are called theta and those yielding 3 mesons are called tau. This I explained last class. Tau and theta are identical twins, for example, of same mass and same lifetime. I hope you might have heard the twins. Twins like a boy and girl, you can distinguish. Twins of 2 boys, twins of 2 girls. It's difficult task to identify them unless you know some characteristic features of either behavior or their characteristic features. They has to distinguish. Otherwise, it is difficult task even on human being. Okay, you right side you see that theta leads to the emission of the 2 pi, tau leads to the emission of the 3 pi. Theta gives even pi, even parity. Tau gives odd parity. Even pi is a mirror image. Odd pi is not a mirror image. Theta gives the even parity with symmetry. Or tau gives odd symmetry. In the sense, being an odd symmetry, violation of the parity. Being an even symmetry, the validation of the parity. Even among the mesons, some mesons will are accepting or following the parity. No violation actually. Okay, parity gets conserved. But thing is that these two gets interchanged in a nucleus of a nucleon of a nucleus, such a way mesons always change from one phase to the other phase. That we'll see next slide. What happens here? That decays into two or three pi mesons are permitted by theory, and therefore it is nothing a surprise. But the two decay modes cannot be reconceived. This is you can't go back actually. Theta can be converted into 2 pi. 2 pi cannot be converted into theta with the law of conservation of parity. That is the thing actually. For example, if you heat water, gets vapor. If you condense vapor, if it becomes liquid form of the water again. If you convert one to an A to B, maybe again maybe A to B to A should also be a possibility to achieve actually. Then we can call it as a conservation. Tau decays to an odd number, pi with odd parity, theta to an even number with pi measures of odd parity. If one of them observe the conservation of parity, either of them, the other must violate it. This is happening so fast you can't distinguish. So deeply rooted was this conception of parity that the physicists involved in the K mesons problem were greatly puzzled by this riddle. The recapture of the atmosphere, that frustrating period was, I might quote, this was a statement made by Wu only. I, in the sense, Wu here. Wu quote Dr. C.N. Young, who said that the physicist at that time was like a man in a dark room, groping for a way out. Groping in the sense, searching for a way to go out from a dark room. He is aware of course, he can use she also, doesn't matter, he or she. He is aware of the fact that in some direction, he in the sense Young is aware of the fact that in some direction there must be a door which will lead him out of his predicament. But in which direction he has to go out of the room in a dark room, we are not sure of it. That is a question. After the parity experiment in polarized cobalt 60, nuclei showed definitely that both parity and charge conjugation in beta decay were violated. In the sense, charges are also not maintained. Parity also not maintained. Violation of the parity as well as violation of the charge conservation, we can call conjugation together. But I violated. Young telegraphed at the time when the communication was through telegraph, the new telegraphed the news to the Oppenheimer. You know that one person who was responsible for the nuclear bomb, who was on vacationing in the Virgin Islands. He came back, he cabled back, walked through doors. He questioned actually. I could not able to find a door. Walked through door, referring to Young's above comment. Walked through door in the sense they found means supporting the work what he had. What he had. That is the case. I shared once. Science is not in silence. Parity violation, one has to accept that. She worked for some project called the Manhattan Project of beta decay. There is a P violation, P violation, C violation, T violation. They can call CPT. One is for parity, one is for charge, another for time. CPT violations makes for particularly the understanding the what called nuclear structures. I will stop at this moment. I will take exactly by 11 because I need time to record this. You just